Hello and welcome to this quite applied first year equilibrium exam question. Because all of it is quite difficult, I'm going to deal with each part separately and do the mark scheme for each part separately as well. The first part is to do with calculating Kc. The second part is about making predictions about observations you'll see and position of equilibrium shifts. So let's take part A and have a look at how we might process it. So it gives you quite a bit of information. It mentions two previously unseen equilibria, and it also then gives you some equilibrium mixture mole data at the bottom to process. Now the first thing is it says equilibrium 1 is set up with the equilibrium position well to the left. That follows the first sentence, which says iodine is a grey-black solid, an observation you might want to bear in mind for later on, that is not very soluble in water. So you wouldn't expect very much of this to dissolve to make I2 aqueous. So that means the position of equilibrium is quite far over this side rather than this side. Hence why it says the equilibrium position is well to the left. So that means there's a greater quantity of iodine as a solid than iodine dissolved in water. However, it goes on to tell you that solid iodine is much more soluble in an aqueous solution of potassium iodide, Ki. Now, Ki is a source of I-, isn't it? Because the word iodide within that would suggest that the iodide ion, which is I-, is present. So the reaction that's going on here is the I2 reacts with I- to make I3-. And it's also an equilibrium. So this time, there's a greater quantity of I3- dissolved in water, when I2 solid is dissolved in Ki aqueous, because the I3- ion tends to form in aqueous solution. So the next thing that happens is a student dissolves I2 in Ki. Now they've just told you about what happens there, so you can predict what's going on here. Now looking at the iodine and the I3-, you can see that this time round there's a much greater quantity of I3- dissolved, 1.96 times 10 to the minus 3 moles, compared to I2, 4.00 times 10 to the minus 5 moles. That suggests that equilibrium 2's position this time lies well to the right, compared to that of equilibrium 1, where it told you it lies well to the left. Now we've had a think about what we're reading, we can use this information, what we've thought about, to calculate Kc. Now I've got to be a bit careful, remembering obviously what equilibrium 2 represents, and also looking at the numbers that have been provided. They're not quite ready to go into a Kc expression yet because they have to be converted into concentrations. They're only moles at the moment. So the connection between moles and concentration is through volume. Now it tells you that the volume is 200 centimeters cubed, but we need it to be decimeters cubed because concentration is in moles per decimeter cubed. So therefore you have to convert to decimeters cubed by dividing it by 1,000. So I'm going to stick to 3 significant figures for now because 200 is the same as 3 sig figs. So 0.200 would be 3 sig figs. So the first thing to do is to draw out my Kc expression with concentration terms for the product at the top and the reactants at the bottom. Now I can put in my numbers applying C equals N over V, so the number of moles I get from the question, and then 0.200 is what I divide that by. That converts those moles into concentrations for me, like this. Now multiplying the two values at the bottom together in the denominator, we now have a much more simplified expression, and we can just plug that into a calculator. So that gives us quite a long number, lots of decimal places. So they want us to do an appropriate number of significant figures. So looking at the data, you've got 3 sig figs for the 200, 3 sig figs for the 4.00, 4 sig figs for 9.404 and 3 sig figs for 1.96. So the least sensitive or lowest number of significant figures in the data provided is 3. So that's what I should apply. Now, if I also need to do my units, what do I do for that? Well, I put in moles per decimeter to the minus 3 for each of the 3 concentration terms. And cancelling through top and bottom will give me mole to the minus 1 decimeter to the power of 3. So let's have a quick look at the mark scheme check and where some mistakes might lead you to. So you can see that if we got 104 decimeter to 3 mole to the minus 1, it doesn't matter whether you say mole to the minus 1 decimeter to 3 or decimeter to the power 3 mole to the minus 1. They don't worry about that. It's either way around. So any mistakes that are made, if we have a final Kc value, it must be to 3 sig figs for reasons we just explained. So there's about 6 different errors, and I'll try and explain what's happened in each case. Well, this person, they've definitely got the right number, but they haven't done it to 3 sig figs and they forgot to put units in, so they lose 2 marks. This person hasn't put the concentrations in, they've just plugged in the mole values that they were given. So what they mean by times 5, it's the same as dividing by 0.200 like we did. And again, they've forgotten the units, so they've done 2 separate things, so they lose 2 marks. Same problem here, except what they haven't done is to apply the 3 sig figs. So they've made 3 mistakes, so they only get 1 mark out of 4. Now this one at the top, they've divided by 5 instead of multiplied by 5. So they haven't put units either, so they've done 2 mistakes, so they lose 2 marks. So this person has put Kc the wrong way around, but they've used the correct concentrations. So they've forgotten their units and Kc was back to front, so therefore 2 mistakes, so 2 marks lost. Now this person has used Kc upside down as well, but in addition to that, they haven't multiplied by 5 for their concentrations. Neither have they done the units, so they've made 3 mistakes separately and unrelated to one another, so they lose 3 marks. Now it's interesting to note that in the mark scheme, if your Kc value is wrong and your Kc expression is upside down, the units will also become different to what you're expecting. You'll have moles per decimeter to the minus 3, not moles to the minus 1 decimeter to the power of 3. So that's an ECF that's applied. So let's now have a look at part B. So the student adds an excess of aqueous silver nitrate to the equilibrium mixture, and they ask you to predict what would be observed and explain that in terms of both equilibrium 1 and equilibrium 2 and any species that are formed. So this is talking about the chemistry of what's going on rather than actually calculating anything. So silver nitrate, you may recall, reacts with I- in aqueous solution to give a yellow precipitate of AgI. So what's happening is the silver ions, Ag+, are what react with I- to give you AgI. The nitrate part doesn't participate in the reaction, it's a spectator ion. So it also tells you that the silver nitrate is in excess, so that means there's enough to react with any iodide that's present. So looking at equilibrium 1 and equilibrium 2, what we need to think about is what's present. Well, we have 4 different things floating around. We have I2 as a solid, we have I2 dissolved, we have I-, and we have I3-. So only this one here will actually react with silver nitrate. So look where this comes from. This comes from equilibrium 2. So equilibrium 2 will actually kick this sequence off now. It's not equilibrium 1. This is where this is a bit applied. You might think equilibrium 1 and 2, they must be number 1 first and number 2 second. Actually, it's number 2 that occurs first, because that's where the silver nitrate goes for the I-. First thing to do when constructing your answer is to state what actually happens. So the reaction of I- with AgNO3, you can use Ag+ as a species here instead of just AgNO3. It saves you having to write out NO3- on the right hand side. So this is perfectly acceptable as an ionic equation. Now, that's present in equilibrium 2. So the next thing to do is, what's the effect of that? Well, equilibrium 2, the position will shift to the left to replace the I- that was removed. And at the same time, more I2 aqueous is made. So what I've just done here is state which of the two equilibria is affected first. Now, because I'm making more I2, I'm increasing the amount of I2 in concentration here. And Le Chatelier's principle would suggest that equilibrium 1 would also shift to try and oppose that somehow. So what's going to happen is more iodine as a solid is going to be made. So position of equilibrium 1 will also now shift to the left to use up the added I2 that was made in equilibrium 2. So more iodine solid is made because the I2 aqueous is now in excess and comes out of solution. In other words, this shifts to the left. So this shows as a black solid or precipitate. So what I'm doing here is I'm describing the effect on equilibrium 1 plus the observation that I see. So let's now take a look at mark scheme for part B. So let's go through each of the marking points and just cross-reference them to what we did. First one is to state the reaction of I- with AgNO3, and we did the ionic version, so we get that mark. We also stated that the yellow precipitate forms. That's the observation. So what happens as a result of this? Equilibrium 2 shifts to the left, and as a result of that, equilibrium 1 shifts to the left. And what is the observation that you see as well? You can see that you have to put in the observation, not just the fact it shifts to the left, but also somehow that you've seen what I2, or predicted what you would see when I2 as a solid is made. Okay, hopefully this has been a useful look at quite a difficult question actually. Doesn't really let up at any point, so this would most definitely be A* standard. But it's nice to have a look at these types of questions from time to time and just unpick them carefully and see how really they're fairly straightforward. You just have to keep a nice cool head about it and just apply logic as you go. Okay, as always, thanks for listening. Until next time, see you soon.